Good day, class. Welcome back to my channel. Please, if you haven't subscribed, kindly subscribe, like, share, and comment so that these videos will get viral for people to also watch. Today, our class we are starting with binomial distributions, and then we are saying that binomial distribution is a discrete probability distributions used to model experiment consisting of sequence of an observation of identical and independent trials, each of which result in one of the two outcomes, right? So we are trying to say that this binomial distribution is a discrete probability distributions, right? And it has what observations, and these observations are independent what trials, of which these trials result in the two outcomes, right? But before we continue, I would like us to go through some properties, some requirements for a binomial experiment to become a binomial distributions. So we are having a binomial this requirement, right? So it states that a binomial experiment is a probability experiment that satisfies the following four requirements, right? So first, there must be a fixed number of trials. Before this experiment can be embarked on, we have to have our fixed number of trials, our fixed number of experiment that we want to get to, right? So always this trial must be always have a fixed number of terms. And second, he said each trials can have only two outcomes, right? Each trial, the trial that we are saying that it should have a fixed number, it has to have only two outcomes. And these two outcomes is success or failure, as you can see down here. And the three, the outcome of each trial must be independent of one another. So at the end of the day, what you are trying to say here is that once it's independent of one another, right, the occurrence of one does not affect the occurrence of the other, right? So that is how it is. And then we have what we call the probability of success must remain the same from trial to trial. So when we are moving from one trial to another, this probability of success must be static. This probability of success must be the same. The probability of success is not supposed to change. So after all these four requirements is being achieved, then you can say that the outcome of binomial experiment and the corresponding probabilities of this outcome are called a binomial distribution, right? So let's go and work. Let's go so that we will go through the PMF for binomial distribution. So that when you get binomial distribution questions, we'll be able to do it. We will learn the PMF and the mean and the variance of these probability distributions. So as you can see on the screen, this is binomial distribution formula, right? That's the PMF that we can use to solve binomial distributions questions. So we are saying that P of x is equal to n combination x, p raised to the power x, q raised to the power n minus x, right? So this is the PMF for binomial distributions. And this same thing, as you can see here, can be written as this, right? N combination x, p raised to the power x times 1 minus p all into bracket n minus x, right? And we know that our q, right? We know that our q, right? Our q is equal to 1 minus p. So I just substitute the q with 1 minus p. As that's the reason why you can see this here, right? And at the end of the day, in some books, binomial distributions is not expressed in this form, right? They are rather expressed in this form. But how do they get this expression? So I'm going to walk you through how they got this expression, right? So that you can use either ways to solve your question. But the most simplest one is this one, right? And the most simplest one is this one, as you can see. But I have to walk you guys through this so that you also know how it came about, right? So here our n combination x, right, traditionally is equal to n combination divided by n minus s combination times s sorry, it's not combination, n factorial divided by n minus x factorial times s factorial, right? So this is how you can express the n combination x as this one. So once you express that this form, then you come and then replace it here, right? So in one way or the other, you can use this one as your PMF, right? Probability mass function to solve your binomial distribution questions, or you can use this one as your PMF. To me, I think this first one, the first one is more simpler, right? The first one is more simpler than what the second one, right? Because for the first one, you can just point n combination x on the calculator, but if you want to point the whole of this one on calculator, it will take you a lot of what your time. And this same thing can also be written as what this. I think I didn't finish this one, so combination times, or either you can use point times what x what factorial, right, times x factorial. So you can write this one, this whole thing in this form, or you can write this whole thing in what this form. So this is what the PMF for binomial what distributions, right? So the n, as you can see in the n is what the number of what observations, right? And then the x is what the number of success in what n trials, right? That's the number of success in what n trials. And p is what probability of a success, where this probability of success lies between 0 and 1, right? And then the q is what probability of what failures, right? Then we have what mean and what variance of what binomial what distributions, right? Sometimes they can ask us in our question to find the mean and then variance of what probability distributions, binomial distributions. So the mean and variance of binomial distribution is just let's say expectation of x is what n times what p, right? That's the number of observation times probability of what success, and this one is always fixed. It will never change, right? That's n times p. So here, once you get your n, the number of observations from the question, and you get your probability of success from the question, you just multiply them together to get your expectation. And the variance too is equal to the number of observation times probability of success times probability of what failures, right? So this is how we can also find what our variance, right? And then you can see that our n here, right? Our n here is what the same number of observation, probability of success, and probability of what failure, right? But they can still ask us to find what the standard deviation, right? The SD of what x. The standard deviation is just equal to what square root of the variance, as you can see, right? The standard deviation is just what square root of what the variance, right? So let's go through some example for us to really appreciate the formulas for the binomial distribution, so that when we get questions, you will be able to go through. So this is our first question. Say a coin is tossed 3 times. Find the probability of getting exactly what 2 hairs. So this coin is tossed what 3 times. So you have find the probability of getting exactly what 2 hairs. And then you see that this question can be solved in 2 ways. You can use binomial distributions to solve this question, and at the same time you can use our random variables, right, to also solve this question. So for us to really appreciate what is going on here, I would like us to visit our our sheet, so that we can really enjoy what is going on there, right? So at the end of the day, they told us that a coin is tossed 3 times. You should find the probability that exactly 2 hairs appear, right? So you see that when the first coin toss, right, this is what we will get, right? And then we will take another coin and then we will toss it separately, right? This is still, you are going to get a head and a tail. If you pick a second coin on itself, right, just a second coin and also toss, you are going to get a head and tail. And if you pick another third coin and toss, you are still going to get a head and a tail. Right? What about when you toss all these 3 coins together, right? The sample space is going to change, right? So right now I'm going to multiply x1 by what x2, right? When you are doing the multiplication, this is how you do it, right? So here, when you come here, you just write here to do what x1, right, h and then t, and the top here will be for x2, right? So I'm just going to multiply. So this time this one is going to give us h, head times head is going to give us head, tail times tail is going to give us tail and tail. Tail times head is going to give us tail head, and tail times tail is going to give us tail and what tail, right? So if you want the sample space for tossing a coin twice together, we are going to get h, that's head, tail, tail head, and what tail. So that's how you outcome, you got this one as our sample space when 2 coins are tossed together, right? And then when we want to when we want to toss all the 3 coins together, we have to do for the first two, and then you add the second one to it. So when you added the second one, right here, the top one is going to resemble what the N one, that's the HH, HT, TH, and then TT, right? And then this part is going to correspond to what the S3, right? Here you got our S3 to what H and what T, right? As you can see here. So here will be H and T. We are just going to multiply them. So this time this is going to give us what HHH. This time this is going to give us HHT. This time this is going to give us HHT. This time this is going to surely give us ATH. This time this is going to give us, right? There is a mistake here. Let me change it fast so that we can continue, right? So here is supposed to give us H and TT, right? HTT, right? And here we are having THH. Is going to give us this, and then this time this is going to give us that. This time this is going to give us that, and then this time that is going to give us what this, right? So if you really want to, after this is how our sample space will be, right? This is how our sample space will be. There's also a mistake here. Let me correct it fast so that we can continue. It's supposed to be HT, right? It's supposed to be HT, right? So at the end of the day, this is how our sample space will be, right? And then the question it was trying to tell us that we should find the probability of getting exactly what 2 head, right? We should find the probability of getting exactly what 2 heads. So exactly 2 heads means that we want a combination that have only 2 heads, 2, right? If the combination doesn't have 2 heads, we are not going to consider that combination, right? But here you see that our sample space is 1, 2, 3, 4, 5, 6, 7, 8. We are having 8 observations, right? And if you want to find the probability that we have exactly 2 heads, it's going to be the number of heads exactly 2 heads divided by the total observation, right? So here, this one is 1, right? It's having exactly 2 heads. We have 1 here, 2 here. We are having 2, and then we are having 3, right? So at the end of the day, we are just having 1, 2, 3, right? So it's going to be 3 divided by 8. Since it's we are calculating what probability is the number of the event divided by the total sample space, and the number of events here is 3, and the sample space is 8. So we're going to do 3 divided by 8. But sometimes you see that this is very lengthy, right? But you can also use this direct way, like using the the binomial distribution to solve this question, right? So when you come back to this sheet, you are trying to say that a coin is tossed 3 times, right? Find the probability of getting exactly 2 heads, right? So if a coin is tossed 3 times, our n is going to be 3. Because we flip the coins how many times, right? That's our number of trials, right? So n is going to be 3, right? And then if you flip a coin, the possibility that we have is probability of success and probability of failure, right? So what's the probability of getting a head? Exactly 2 head, right? So we think that we are our concentration on the head. So here, since we have 2 outcomes, right? Our first probability will be 1/2, right? So if you have 1/2 for the p, our Q2 will be equal to 1 minus 1 p, which is 1 minus half, which will give us what? Which will give us what? 1/2, right? So let's come back to our sheet so that we will really appreciate what I'm trying to say, right? So here, our n from the question, our n will be 3, right? Our p will be given as half, because if you flip a coin 3 times, right, either for the outcome you will either get a head or a tail, right? And they told us to exactly they told us in the question that we should find the probability of getting exactly 2 heads, right? But here you can see that we are having our head here, so here our p will be the total sample space here is 2. Sorry, our n here is 2, and our concentration here is on the h. So here it will be the number of observation divided by the total sample space, which is 2. So here our p is going to be half. If we want K02 will be 1 minus p, right, which will give us 1 minus half, which is half, right, as you can see there. So at the end of the day, you could see that we have our probability of what success here, and what our probability of what failure, as you can see here, and our n is 3, right? Our x was given inside the question. He said we should find the probability that exactly 2 here, right? So exactly 2 here will be our x here will be equal to 2, right? So here we want to find our probability, right? He said find the probability of having exactly 2 here. So here it will be p into bracket x is equal to 2, right? Which is equal to sorry, here is supposed to be here is supposed to be probability of x is equal to that, and here is supposed to be probability of x is equal to what, 2, right? As you can see. So right now we have to write down our PMF for binomial distributions, right? You have to write the PMF for binomial distribution, and our PMF for binomial distribution is what, n combination x p into brackets, right? N combination x p into bracket p raised to the power x bracket open 1 minus what p n minus what x, right? As you can see here, right? So at the end of the day, once you have this one, and then we have this our parameters, right? What you do, you just substitute it into this function. So you see that our n, where we see the n, you just substitute 3. Where you see x, you substitute 2. Where you see p, you substitute p. Where you see q, you substitute what, q. Or better still, where you see 1 minus p, you substitute 1 minus p, and then you substitute n and the x. So once you do that, right, once you do that, you are going to get what, this expression, 3 combination 2 half raised to the power 2 times half raised to the power 3 minus what, 2, right? And then when you simplify this one, this is what you are going to get, 3 divided by 8. So that's the same thing for this one, right? So you can either choose to use this one or use that, right? But if you use what, I think the binomial distribution is quite simple than the random. So this is our second question. Our second question is saying that a survey found that 1 out of 5 Americans say he or she has what, visited doctor in a given month. If 10 people are selected at random, find the probability that exactly 3 will have visited what, a doctor last month, right? So at the end of the day, you can see that our p is given here in the question, right? Our p was given in the question here. The p is given in the question, right? And then our n2 is given in the question here, and our x2 is given in the question. So once you have p, definitely you are going to have q, right? So at the end of the day, we see that he said that a survey found out that 1 out of what, 5 Americans. So here our probability of success is 1 over what, 5 people seeing what, the doctor, right? And then if you want our q is just 1 minus what, p, which will give us q is equal to 1 minus what, 5. We are going to get what, 4 over what, 5, right? So we are going to surely get our p to what, 4 over what, 5, 4 over what, 5, right? And then we get our n is here, right? 10 people are selected at what, random. So our n is what, 10. So our n is equal to 10, right? And our x is given inside the question given. He said we should find the probability that exactly 3 will visit our doctor last month. So here our x2 is equal to what, 3. So once you have this preamble, it's very, very easy for you to solve. So let's go to our worksheet, and then let's see how this question was what, solved, right? So at the end of the day, we have our preambles here. The p is equal to 1 over 5, q is equal to 4 over 5, n is equal to 10, and x is equal to what, 3, right? So we have to write our PMF for the probability binomial distribution. So once we write our PMF for the binomial distribution, this is how it will look like, and then just substitute what we have here. So here will be 10 combination 3 into bracket 1 over 5 raised to the power 3 times 4 divided by 5, right, raised to the power 7. So once you multiply this one together, I'm going to get 0.201, right? I've run it to a 3 decimal place, right? In fact, it's I think 4 so decimal place, right? So this is how the second question 2 was solved, right? So let's go to our third question, right? So our third question is telling us that it said a survey from teenage research Unlimited found that 30% of the teenage customers receive their spending money from part-time jobs. If 5 teenagers are selected at random, find the probability that at least 3 of them will have part-time work jobs, right? So at the end of the day, our P2 is given here inside the question, right? So you see that was found that 30%, right? 30% of the teenagers, right? So we have our P here, and then he said that some people were selected in random, right? So always concentrate on the some people, right? Always the N. The some people will be our N, right? Selecting people at random will be our N. So here our N is what, 5, right? And then once we have our P, we surely have our Q, right? And then we use that one to solve this one question at least, right? I will walk you guys through what the at least is, right? So I don't believe we are saying that our P is equal to what, 0.3, sorry, 30%, right? This 30% can be expressed as 30 divided by what, 100, and then we can say that our P is what, 0.3, right? If P is 0.3, our Q will be equal to 1 minus 0.3, and our Q will be equal to what, 0.7, right? And then our N was given inside the question as what, 5, right? And then our X, right? Indeed, our X is at least, right? I want you guys to really appreciate something here before you solve the question, right? I want you guys to also know the at least, at most, the greater than, the less than, so that when some appear in our subsequent one video that we are going to do on this, we will be able to do it, right? So when we say at least, right, when we say at least in mathematics, it's just trying to tell us that it's greater than, right, or equal to, right? The thing is what, greater than or equal to at least. So for instance, we are trying to find the probability that at least 3 of them will be part-time jobs, will have a part-time job. So here our X will be what, greater than or equal to 3, right? So the at least here is what, either what, greater than or equal to, right? Greater than or equal to. So here I'm going to start from 3 to what, up to what, 10, right? Sorry, 3 up to what, 5, right? So here the at least here is what, greater than or what, equal to, right? And then the limit of X will end at what, our N, right? So we are going to move from what, 3 to what, 5, right? What about if we are asked of what, at most, right? So at most 2 is what, less than or equal to. The at most is what, less than or equal to. So here our X will be, let's say, if in this question find the probability that at most 3 of them will have part-time jobs, and here will be at most will be, X will be less than or equal to what, 3. So we are going to start from 0 up to what, 3, right? So that's for the at least, and what, for the at most. What about the less than, right? So the less than and then for greater than, I think we are familiar with what, less than and greater. So since we have our P and our Q, I think we can go back to our worksheet and then solve this one nicely one day. So that's our question 3. So our N was 5, our P was 0.3, Q is 0.7, and what, our X is equal to 3, 4, and 5, right? So we are going to find the probability that our X is greater than or equal to 3, right? And then our N here was what, 5. So we are going to end exactly at 5, right? If our N here was, let's say, 7, then we are going to move from what, 3 up to what, 7, but here our N ends at what, 5, right? So here we have probability of X is equal to 3 plus probability of X is equal to 4 plus probability of X is equal to 5. So we are going to solve them individually, and after that you add. So yeah, probability that X is equal to 3 is here, right? So we're just going to substitute it into our formula. So here will be 5 combination 3 into brackets 0.3 raised to the power 3 times 0.7 raised to the power 1, 5 minus 3, right? So we're going to do same for the 4, and we're going to do same for the 5, right? So as you are going, you see that the thing will keep on what, decreasing, right? So here we are going to have, when you write the one, you are not writing here, but I want to write this so that you get it. Right? We are going to write 5 minus what, 4, and here 2 will be 5, right? 5 minus 5, right? We are going to have 5 minus 5, right? Since our N was 5 and our X was 5, so here will give us 5 minus 5, right? So let's simplify it to its simplest form. So once you simplify it, this is the expression that you are going to get. You point all of these things on calculator, and you're surely going to get your 0.162, right? So at the end of the day, that is how this question is being solved, right? So let's walk through a typical example on mean and what variance, right? So for example, if you have this question, right, say that a coin is tossed 4 times, find the mean, variance and standard deviation of the number of heads that will be what obtained. So if a coin is tossed 4 times, our n will be what? Our n will be what? 4. That's the number of what trials, the number of times this observation is being tossed, right? And then our p, as I told you, our p will be surely be half, and our q will be also be what? Half, right? Because if you toss a coin 4 times, first one, if you remove a coin and toss, you are going to get a head and a tail. The second, right, you are going to still get a head and a tail. For third, you are still going to get head and tail. And then oh, I'm coming, sorry. And then for the fourth one, you're sure going to get head and what? Tail, right? So at the end of the day, you see that we are having head and tail, right, for each of the individual trials, right? But if you want to perform all these things together, right, the number of times this x1, s2, s3, s4 was tossed together there, we are not going to get x1 as you see the head and the tail, head and tail, no, right? It will give us a big sample space, right? But this is how it is. So what's the probability of getting a head, right? It's just 1/2. When you come here, it's 1/2. When you come here, it's 1/2. Here, when you come here, it's 1/2. So that is how it is, right? So here our n will be that, our p is this, and our q is that. So let's go to our worksheet so that we really solve it there for you guys to appreciate, right? So here our expectation will be equal to what? N times what? P, that's the number of observation times what? Probability of our success. So here and then you see that for the p is the half is equal to a 0.5. So you can choose to write a half or 0.5, right? So here our n is what? 4, and our p is 0.5. We are going to get 2. Right? Just punch it inside the calculator. We are surely going to get this one. And then if you want the variance is 4 times 5, 0.5 times 0.5. Since you are having number of observation times what? The p times what? The q. As we have in here, your final answer is going to give us what? 1. And then you told us to find the SD, right? So s dot d is surely going to give us square root of what? The variance, right? So here our variance was 1, so square root of 1 is equal to what? 1. So our standard deviation 2 is what? 1, right? Our standard deviation 2 is what? 1 here. So at the end of the day, this is how the mean and variance can be solved, right? So I think this is our last example that you guys will be going through, right? After this, we will bring the class for binomial distribution to an end, right? So here we are saying that a coin is rolled 360 times, right? Find the mean, variance and standard deviation of the faults that will be rolled, right? So at the end of the day, our n here, right, our n here is giving us what? 360, right? Because that's the number of trials. So 360. So we have this one, 360. And our p is equal to 1/6, our q is equal to 5/6. I'll teach you how we got it, right? So that's the same similar example for what we are doing. The same similar example, right? So here this is not rather a coin, but it's rather what? A tail, right? Sorry, it's rather what? A die, right? A die is called a root 360 times, right? So it's rather a die, sorry, not a coin. So I know you could see that our p is equal to 1 divided by our 6, right? Because for a die, right, the possible outcome that you get is what? 1, 2, 3, 4, 5, 6, right? What's the and then we want us to find the variance, but you see the probability of getting a fourth this thing is what? We are just having only 4 here, right? And it's 1. So if you get the probability of that is equal to what? The number of number of events divided by what? Number of the sample space. So you are going to get p to what? 1/6. We are going to select 4 out of all the sample space. We are going to get 1/6, and our q here is what? 5/6, right? So that is how we got our p and then q. Once we get our p, right, we are going to just subtract it from 1 and then get what? Our q, right? So once we have our n, p, and q, our this thing will be very simple. So expectation of x is equal to n times what, p, right? Here we are going to get 360 times 1 over 6, which is what, 60, right? Because expectation is what, number of deviation times what, probability of success, of which we get this here. And then for the variance, it's going to be the number of trials times probability of success times probability of failure, of which you are going to get 360 times 1 over 6 times 5 over 6, of which you are going to get what, 50, right? So this is how this thing will be, right? I'm sorry, I'm making some small mistakes in this video I'm making. I'm very sorry. Let me correct that, right? Because here I'm going to get 360 times 5 over 36, right? So this one will cancel this how many times? I'm going to get about let's say 10, right? 5 times what, 10, right? And then surely still we are going to get 150. Yeah, surely still we are going to get what, 50, right? So this is going to give us 50. And then once we want the SD, just square root of what, the variance. And then once you square root the variance to the square root of a variance, to the square root of what, 50, right? So once you put it on calculator, it will reduce it to what, its simplest form for you. So this is our end of for our binomial distribution class. Take your time and go through the formulas and walk through the example. Everything will be fine. Thank you for watching. Kindly subscribe, like, and comment. Thank you. Bye.